So in this video, I want to go over the kinematic equations, but first let's go over this first kinematic equation, this displacement formula. And this kinematic equation looks very complicating, it looks very intimidating with a lot of variables and a lot of these terms squared. What's going on? It seems complex. Well, it's really not so bad. And first, let's focus on a simplified version of this displacement formula. So the simplified version of this equation is that the distance an object travels equals 1/2 times the acceleration of the object multiplied by the amount of time that object was accelerating for. So if you know an object's acceleration and you know how long it was accelerating, you can determine how much distance, how far it traveled, how much distance it traveled. So what do I mean? So let's do an example. So let's say we have this Corvette. Let's say we have this car. And let's say it has an acceleration of 1 meters per second squared. And let's say it's doing that acceleration of 1 meters per second squared for 1 second. If we had a Corvette with that acceleration, accelerating for that 1 second, how much distance, how far would it have traveled? Well, the first thing we need to realize is, what is acceleration? What does it mean if we have an acceleration of 1 meters per second squared? Well, an example is maybe initially this car was not moving. Maybe it had a velocity of 0 meters per second squared. But maybe 1 second later, then it was traveling at 1 meters per second squared. Then maybe another second went by. Then it was traveling at 2 meters per second squared. Then another second went by. Now it's at 3 meters per second squared. This would represent an acceleration of 1 meters per second squared. Because the velocity increased by 1 meters per second. And again, remember what an acceleration is. It's a change in velocity. So we saw the velocity increased by 1 meters per second. Every second that went by, the velocity increased by 1 meter per second. So that's what an acceleration of 1 meters per second squared. So if we had a Corvette with this acceleration and it had that acceleration for 1 second, how far would it have traveled? What would be the distance it covered? Well, again, we know we could simply determine that using this equation, using the simple displacement formula. The distance traveled by an object equals the acceleration the object had multiplied by the amount of time it was accelerating for. So if we were to do this and just plug in all these terms, and remember the equation is 1/2 acceleration times time squared, we would essentially get this equation. And then we would just solve this. And we would get roughly around 0.5 meters. So if we had a car with this acceleration and it was accelerating for 1 second, it would travel 0.5 meters. But let's do another example. Let's say we had another car, and let's say it had an acceleration of 2 meters per second squared. What does that look like? Well, again, maybe initially it was at 0 meters per second, then 1 second later it was at 2 meters per second, now another second later, now it was at 4 meters per second. So this represents an acceleration of 2 meters per second. The velocity increased by 2 meters per second per second. So that's an acceleration of 2 meters per second squared. And again, the acceleration tells us how the velocity changes. So if you had an acceleration of 2 meters per second squared and we accelerate of that acceleration for 6 seconds, how much distance would we cover? And it makes sense that we would cover more distance than this first example because we have a higher acceleration and we were doing that acceleration for a longer period of time. So again, we can determine that using this equation. As long as we know the acceleration of an object and we know how long it was doing that acceleration, we can determine how far it traveled, the distance traveled. So in this example, we would get 36 meters. The distance traveled by this car in this situation would be 36 meters. However, something really important to realize is this formula is a bit of a simplification. It's actually not quite the truth. So why? Why isn't this accurate? Well, let's do another example. Let's say we have this car, but let's say its initial velocity, let's say initially it was at 0 meters per second. It had no velocity. It was standing still. And then let's say this car that was standing still suddenly had an acceleration of 1 meters per second squared. And let's say it was doing that acceleration for 2 seconds. How much distance would it cover? Well, again, first of all, let's analyze what's going on. We know initially it was at 0 meters per second. Then 1 second later it was at 1 meters per second. Then another second went by. Now it was at 2 meters per second. And again, we explained that was the acceleration, so that's what's going on. So therefore, we do this kind of acceleration for 2 seconds. So how much distance would we cover? Well, again, we simply just use this equation. So if we were to plug in this car's acceleration and the amount of time it was accelerating for, and again, that gets squared, we would get a distance of around 2 meters. And does that make sense? Is this a reasonable answer? Well, yeah, we know on average, this entire 2-second time period, it was traveling on average around 1 meters per second. The first second it was at around 0.5 meters per second. The second it was at about 1.5 meters per second. But during this entire time, the average velocity for this entire 2 seconds was about 1 meters per second. So therefore, it makes sense that we traveled around 2 meters. That makes sense. It's logical. This checks out, and that makes sense. However, what if we had a different situation? So this is a little hard to imagine, but now let's say we had a car that was initially moving at a velocity of 1,000 meters per second. So let's say we had this car that was moving very fast with a velocity of 1,000 meters per second. Then let's say it suddenly started getting an acceleration of 1 meters per second squared. So it's suddenly accelerating, and it had that acceleration for 2 seconds. During that 2-second period, from again the initially when it was traveling at 1,000 meters per second, then we click the stopwatch, and it starts accelerating at 1 meters per second, and we do it for 2 seconds. During that 2-second time period, how much distance was covered? Well, again, we know this equation. We know simply this equation. The distance covered equals the acceleration multiplied by the amount of time. So if we then squared, and again at 1/2, just the way the equation works. So in this situation, we would get a distance of 2 meters. It traveled 2 meters during this 2-second time period. However, does this make sense? Is that reasonable? Well, again, let's analyze this car's motion. We said initially, in the beginning, right when we click that stopwatch for the beginning of that 2-second time period, we know initially it was traveling at 1,000 meters per second. And again, we explained the acceleration was 1 meters per second squared, so every second that went by, the velocity increased by 1 meters per second. So we know 1 second later it was at 1,001 meters per second. Now another second goes by, now it's 1,002 meters per second. But the point is, during this 2-second time period, this 2-second interval, we were traveling on average around 1,000 meters per second. That's an average, but we were traveling around 1,000 meters per second. So if that entire 2-second time period, we were traveling on average 1,000 meters per second, we would travel much more than 2 meters. So this is not right. This can't be right. We are traveling on average 1,000 meters per second for 2 seconds, so we would have traveled much more than 2 meters. So in fact, this equation isn't perfect. It has a limitation. And in fact, we see now that the initial velocity is important, because that initial velocity determines what the average velocity was that entire time period. If we started out with a higher initial velocity, then that entire time period we're traveling at a higher velocity, so that's important. That should affect how much distance was covered. So the real equation is this. Distance traveled equals 1/2 acceleration times time squared plus the initial velocity times the amount of time. So again, we see the initial velocity should have an impact on the distance traveled. So it should be involved in this equation. So this is the real equation. This is a real equation. This is really how things work. So again, we see that initial velocity matters. And then if we were to plug in all these terms, this acceleration, this time, which gets squared here, then this velocity, and then again this time, which in this situation doesn't get squared, if we were to plug in all these terms, we would get a distance of roughly around 2,002 meters, which makes sense. That makes sense. We were traveling on average about 1,000 meters per second for 2 seconds. This makes sense. That makes sense. So this is the real answer, and this is the real equation. And however, in this equation, remember, in this example, we did have an initial velocity of 0 meters per second. So again, remember, the real equation is this plus the initial velocity times time. But if the initial velocity was 0, in this example it was, so if the initial velocity was 0, then this would just go to 0, so this entire term would just go to 0, so you could just ignore this. So this equation is true. You can use the simplified formula of the equation when the initial velocity was 0. Because again, that term would just cancel, would just be 0. So if the initial velocity is 0, then you can use this equation. This equation is right. However, if the initial velocity is not 0, then you need to use this equation to determine the distance traveled. But again, so this is the displacement formula. This is the displacement formula. If you want to determine how much distance an object traveled, you need to know the acceleration of the object, you need to know the initial velocity, and you need to know how much time it was traveling for. So this is the real equation. And really, what is a distance? What is a distance? Well, again, another way to represent a distance is just the final location minus the initial location. This is a displacement. We've learned in previous videos, this is displacement. If we have the final location minus it by the initial location, that gives us a distance traveled. So this really equals this. So this is another way of looking at the equation. And notice, this is our initial displacement formula. It's just a little rearranged. I added the initial location to both sides, but if you do some rearrangement, this is the displacement formula. So this is what's going on in the displacement formula. And it looks a little complex and intimidating, but it's not so bad. Really, the point is, if you rearrange it, really all it's saying is you can find the distance traveled as long as you know these variables. So that's the displacement formula. However, another common kinematic equation is this equation. The final velocity squared equals the initial velocity squared plus 2 times the acceleration of the object multiplied by the distance traveled. And all these kinematic equations, even the previous displacement formula, assumes a constant acceleration. But so we have this equation. This is another common kinematic equation. So let's do an example. Let's say we have a ball. Let's say we have an object, and let's say we drop it. Let's say we were holding onto this object, and we suddenly dropped it and let go. We know it would start accelerating downward. We know there's a force of gravity. We have a force of gravity which would force this object down, and we know from common day experience, we know the object would fall. It would start falling, and it would start accelerating downward. So we know it's moving downward, and let's say it starts moving, and let's say once it's traveled 30 distance, 30 meters, we dropped it, and it traveled 30 meters. At the 30-meter point, what would be the velocity of the object? What would be the velocity of the object once it's dropped and fell 30 meters? How can we determine that velocity? Well, we can do that using this equation. Because if you think about it, we know the initial velocity was 0 meters per second. We were holding it and it was still. So the initial velocity was 0 meters per second. We know the distance that we're interested in was 30 meters. That's the distance. We're interested at the final velocity at 30 meters. So that's the distance traveled. And we know the acceleration is the acceleration due to gravity. And whenever you're doing a kinematic equation, we're always going to have that acceleration of gravity, which is roughly negative 9.8 meters per second squared. And again, it depends on the coordinate system you're using, but if you're assuming downward is negative, then we always have this acceleration due to gravity. And again, we know if we drop this ball, it will start moving. It will have an acceleration downward. So whenever you're dealing with kinematic equations and you're dealing with these vertical accelerations, there's always never forget that acceleration due to gravity, which is around negative 9.8 meters per second. So now, if you think about it, we know these three variables. We know the initial velocity was 0 meters per second. We know the acceleration of gravity, and we know the distance traveled. So we know three variables. So now we can solve the final variable, the final velocity at the end of that 30-meter distance. So usually that's how these kinematic equations work. You'll have all the variables besides one, and you would need to solve that final variable. So just doing some rearrangement, we could essentially do the square root of both sides. If we did that, we would have the velocity final equals the square root of the initial velocity squared plus 2AD. And if you were to plug in all these terms, the initial velocity of 0 meters per second, again, this is just 2, and then you plug in the acceleration due to gravity, and then you plug in the distance, you would get a V final. You get a V final of roughly around 24 meters per second. So that's the final velocity. At that distance of 30 meters, that final velocity, it would be traveling at around 24 meters per second. And if it's going downward again, that would be negative 24 meters per second. But again, so essentially that's how you use this equation. So this is another common equation. And another example you'll see with this kind of equation is this, where essentially you have an object, but this time you throw the object upward. You throw it upward with the initial velocity of 10 meters per second, going upward. And we know what's going to happen. We know there's a force of gravity accelerating it downward, so we know it's going to go up, then eventually it's going to drop. And we know that entire time we're going to have that acceleration downward. Because again, what is an acceleration? It's a change in velocity, and we know the velocity is constantly going to go more downward. Initially, it's going up fast, then it's going up slowly, then it's standing still, then it's going down, then it's going down fast. So that entire time, it is accelerating downward due to that acceleration due to gravity. But again, so we throw this object upward with an initial velocity of 10 meters per second. It reaches its peak, and then it starts dropping. What is that peak, though? What is that distance? That peak, once it reaches that top, and then it starts falling downward, what is that distance? What is that top peak? This seems like a very complex question with a lot of critical analysis. How can you determine that top peak once it starts falling downward? Well, you can simply use this equation, where again, we know the initial velocity. In this situation, remember, we initially threw it at 10 meters per second, so we know the initial velocity. We know the acceleration is the acceleration due to gravity. We're dealing with these vertical accelerations, so we know that it's the acceleration due to gravity. And we also know the distance, or we want to find that distance. We want to find how far it traveled, but to determine that, we need to know what the final velocity was at that distance that we're interested in. And again, what is going to be the final velocity? Once it reaches its peak, and then starts falling downward, what is going to be, once it reaches that peak, that final distance, that distance that we're interested in, what is its final velocity going to be? Well, this is a trick you need to be familiar with kinematic equations, but whenever something goes upward, then it starts going down. Once it's at that peak, its velocity is 0. It's not moving. It reaches that peak, then it starts moving downward, but when it's at that peak, its velocity is 0. So if we chose that at our final velocity, that velocity at that final location we're interested in, what's going to be that distance? What's going to be that distance? And now we know all these terms. So again, we know the final velocity was 0 meters per second because again, that was the final distance that we were interested in. So that final velocity again it's not moving, so 0 meters per second. We know that initial velocity was 0 meters per second, and we know the acceleration is negative 9.8 meters per second squared. So again, we could just do some rearrangement. Final velocity squared minus velocity initial squared, essentially divided by 2a equals distance. So if we were to just plug in all these terms that we know, and we know all these terms, this would just be 0, that final velocity. This would be the initial velocity, so that would be positive 10. And then 2 times acceleration of, again, negative 9.8 meters per second squared. We would get that distance. And that distance would be roughly around 5 meters. So that distance, once we reach that final velocity of 0 meters per second, is around 5 meters. So again, this is another common kinematic equation. But it's important to realize to not forget these equations. I think it's very easy to forget the definition of velocity, which is essentially final location minus the initial location divided by time. And again, really this is just distance. A distance traveled divided by time is velocity. So don't forget this equation. Sometimes you need this equation to solve a kinematic equation. And don't forget the definition of acceleration. The final velocity minus the initial velocity divided by time equals the acceleration. That change in velocity divided by time is the acceleration. So don't forget this equation. And if you were to rearrange this equation, if you essentially multiplied both sides by t, so multiplied both sides by t, and then add initial velocity, essentially if you were to rearrange that, you could get this equation. You would get this equation, which again is just the rearrange the definition of acceleration. And notice this similarities, this equation to this equation. Essentially, final velocity equals initial velocity plus acceleration, but instead of distance, we have time. So again, depending on what you're interested in, it may be if you're interested in distance, use this equation. If you're interested in time, use this equation. But notice the parallels and the similarity between these equations, and also notice the differences. This one, it's squared, and this one has a 2. But notice the differences and the similarities with these equations. And again, the way these kinematic equations work and these problems work is you'll be given 3 of the variables, and you'll be asked to solve the final variable. For example, maybe you have the final velocity, the initial velocity, and the acceleration. Then you could use this equation to determine the time.